Hey, what's going on, guys? My name's Jacob Bennett with Bulldog Analytics, and today we're going to be breaking down the star schema data model into terms that hopefully are easy to understand, while also emphasizing the importance of taking this approach, especially when working with large data tables in Power BI. The goal for today's discussion is that this would not be an overly technical presentation, despite the fact that this is a very technical topic. Full disclosure, I'm going to be presenting from my own experience. This is not going to be diving into the history of star schema models or even really comparing it to other data models out there. I really just want to stick to the essentials, do a little bit of knowledge sharing, provide some basic explanations and definitions in terms of data modeling in Power BI, and really just equip you so that you can feel comfortable getting started using star schemas in your Power BI reporting. All right, let's get started. All right, guys, now before we get into the Power BI side of things and see how this star schema model comes together, I first want to take a step back and look at some sample data just in Excel so we can kind of start to grasp how, where this star schema model really starts to improve our performance and help us out in the long run. So as you'll see here up at the top, this is titled Dunder Mifflin Sample Sales Data. It's about 1.2 million rows of data overall for about a 3-year period. Now, just full disclosure, for this Excel document that I'm displaying here, I've stripped it down just to a smaller subset of that, maybe 50,000 rows, just so that performance-wise I can navigate through here pretty easily as I walk through this. But yeah, so let's start looking at this. It's sample sales data. So as you can see here in the first couple columns, we've got an invoice number, which is just made up of an order number and a line number. And then from there, we've got the unit price, the sales quantity, discount percentage, as well as the total sales and a few date columns associated with that line number under the order number. So as far as the required granularity for what needs to be displayed in the data, we really can't get away from the number of rows that exist in the data. So that 1.2 million number I threw out there for 3 years, we can't really get away from that because that is the number of invoice numbers that exist in the data over that 3-year period. Now, if you work for a large organization, 1.2 million, that's nothing. A lot of folks who work with large sales data sets or maybe even inventory logistics, you're working in the hundreds of millions of rows of data. So this topic that we're discussing today applies even more so around creating optimization to improve performance in your reporting. Now I'm going to go ahead and highlight those few rows because to me, these are kind of the core fact table, if you will, when we're talking star schema data model. And we'll get to kind of the definitions around what all that means here in a little bit. But this is kind of that central component, stuff that you can't get away from. This has to exist as it is here. Now, once we move past that data, you can see over next to it, we've got a bunch of customer data and we start to see redundancies. So obviously all of these lines in this order are associated with this Brain Lounge customer. And as you can see, for every customer ID 85, next to it, it lists out the name, customer code, the customer purchaser, their title, address, state, postal, country. So this is all data that's associated with the customer file. I'm going to go ahead and highlight that. Now this is fine, but as you can see here, and this is sorted by the order number and line number, but as you can see, there starts to be some apparent redundancies. These are all the exact same data over and over again. And we can see this even more if I go to data, sort, and let's look at this by customer ID, smallest to largest. Now you'll see, we've got just so many lines of replicated data, just redundant data over and over again. And again, this is only 198 rows of data. Imagine working with really, really large data sets where one customer might have thousands or even millions of order IDs or order numbers associated with their business. And with those thousands of lines of sales data come just thousands of duplicated rows of redundant data that look exactly the same like this across multiple columns. And in this instance, we only have, 1, 2, 3, 4, 5, 6, 7, 8, 9 rows of customer data. In a real world example, you could have 50, 100 plus rows of customer data and related fields that go under that file. So when you think about that, it really starts to become glaringly obvious that that's going to create some implications for your report performance. And we need to figure out a way to optimize that. So Before we get into that, let's look over, we got product data next to the customer data. Let's highlight that. It's going to be a few more columns, I believe. We'll put like an orange color on that. And again, you know, we see the apparent redundancies. So everything associated with product ID 5, let's even apply a filter and kind of see. Every single time we see product ID 5, which in this, you know, sample example, we've got over 3,000, but again, this is going to be a very small example of what actually would be occurring in real world, depending on your business size. But for every time that product ID 5 occurs, it's going to return the exact same results for every other column without fail. That's just the nature of matching up the product ID to its underlying details. You wouldn't want that data to be different. And I'll mention the last piece quickly if I remove that filter. We've also got a supplier dim containing supplier information. And then we've got a shipper dim containing shipper information. Now if I apply a filter and come over to shipper dim, you'll see that only 3 shippers exist. We've got Federal Express, Speedy Express, and United Package. Well, for 1.2 million records of sales data, if we only have 3 shippers, why would we repeat the shipper name and the shipper phone number 1.2 million times if we could just have it stored separately in a table with 3 rows, Speedy Express and its phone number, United Package and its phone number, Federal Shipping and its phone number? That's 3 total rows with 3 columns. You'll have the ID, which acts as a key, which we'll talk here in a second, and then the name and the phone. Rather than repeating it 1.2 million times, that's such a space saver overall, and it's just going to create massive improvements in your report optimization. Now, for those of you that have worked in data models, this might seem very, you know, basic, but I'm just really trying to drive home this point of reducing the redundant data and creating this optimization. So the idea here is that we have our core data here that we can't reduce as far as rows go or columns. These are the required columns we need at the required granularity. And in order to associate a customer, a product, a supplier, and a shipper to these invoice numbers, we need to have some sort of key or something to relate it to, because if I just pull this data in as its own table, there's no way to identify from these available columns right here that I have highlighted which customer, which product, etc. it's associated with. So we'll need a key that allows us to basically tap into all the details of the underlying customer records, product records, etc. So that key in this instance is going to be the ID associated with each of those elements of the data. So we've got this customer ID here. We've got a product ID. We've got a supplier ID. And we've got a shipper ID. I'm just going to highlight those yellow. Now again, every time, for example, the supplier ID equals 30, all of the associated data over here is going to be exactly the same. Every time it equals 7, all this associated data is just going to be repeating itself and be exactly the same. Same with the other dimensions as we're about to define. So because this is the case, we're going to want to also include these IDs in our core table that we're talked about over here on the left-hand side. So let's create a couple of additional spots where we can include that data. I'm going to copy it over. All right, so now everything highlighted in yellow is going to be our central table. It's going to contain all the detail as far as getting down to that line number, but it's also going to provide us everything we need to access any of the other details, like all of the customer fields such as code or the customer purchaser, their title, the address, etc. And then from there we can create what are called relationships in a data model to access that additional level of data beyond just the customer ID. We might want to see the name or the code, like I just said, or just the product ID. We want to see the product name or the product descriptions. So I'm going to switch over to Power BI now, and we can kind of start to see this all come together and it create a lot of optimization and performance improvements in our data. let's take a peek. All right, guys, as you can see, I've got a Power BI report pulled up, and I first want to display an example of the flat file approach that we were talking about a second ago that's not optimized, not super efficient. And you can see here in the model, it's literally just one table. Over here, you've got the orders flat file. It's just all of those tables listed out, all located in one box. It's a little bit difficult to navigate, and again, there's a lot of repetitive data in there that is just super kind of unoptimized and not great for the reporting performance. Now, I think I mentioned this, but this approach is completely fine if you're working with really small amounts of data, or maybe it's just a quick ad hoc report. I totally get it. It's still an option, but we're talking large amounts of data that require optimization. Maybe you have some pretty poor report performance because you've built something this way, and so creating a data model is just the best approach, especially if you're working with a relational database, just so that you can kind of mimic the source. So let's click over to my optimized model that employs a star schema data model. All right, so if you look over in my data pane, as you can see, I have multiple tables now. So this order details table kind of acts as that core table that we talked about in the first several rows of our Excel example. And if I click on the table view over here, you'll see if I click down to the order details table, you know, it's not in the same order as our Excel document was, but you'll see we've got the sales order ID made up of the order number, the line number, all those quantitative elements that we discussed, as well as these IDs or keys, as we're about to define, that allow us to create relationships with the other tables that have been exposed here. So again, we've got those other tables. Now, if you look at the customer table, for example, you've got that customer ID, and then you've got all that additional detail that exists, product ID, all the other details that exist alongside product. There's a few additional here that I didn't have exposed in the Excel document. Additionally, I've also created some date tables. Before, we only had in the order details kind of hub table, we had the order date, the deliver date, and the ship date, which is helpful, but as far as trending by month or by year, there's not like an aggregation component to that. So we have to either create a hierarchy or relate it to a table. So as you can see, these are all actually pretty much duplicates of each other. But if I click on the order date table, for example, you've got that date, which in this instance will act as a key for us to relate to that core table or that hub table. But then, as you can see, you've got several other ways to analyze the data, whether it be year month displayed in a different way, month name, total days in month. There's a bunch of other stuff that in here that allows for some pretty cool analysis. So not going to get into that much right here, but let's go ahead and click down to our data model. All right, so now, as you can see, this kind of takes on that star schema model, also sometimes called hub and spoke. You've got the order details, that kind of core table here in the middle acting as the hub, with these dimensions at the perimeter, and all of them are related to that hub table, to that core table. And as you can see, oh, you know what? The customer wasn't related. So this is a good example. We can drag the customer ID on top of the customer ID, and it'll establish a relationship. And that's how all these are structured. If I click on it and I go over to the properties pane, which we break down this model view in pretty good detail in a separate video I made, so please feel free to check that out. But it'll show that it's related from the supplier ID and the supplier's dim table, dimension as they're called, we'll define that here in a second, to the supplier key in the order details table. Now, my keys and IDs here aren't really standardized, so that's probably not a good practice, but I think you kind of get the idea. You've got the product ID to product ID, shipper ID to shipper ID. You've got the dates related on the actual date fields in that core table themselves. You'll also notice, if I zoom in here a little bit, when you look at the relationship lines, there's this asterisk for every line coming out of this core table, and then there's a 1 for all the dimensions. Now that indicates a many-to-one relationship, and that makes sense because the core table contains that granularity, that detail, to where, as mentioned, you know, there'd be some redundancy, some level of redundancy for customer records, for example, or product records, where there's going to be multiple lines associated with a single product, multiple lines associated with a singular customer. And so the whole idea is to create a table that only contains one record per customer, one record per product, etc., and then be able to relate that to the core table in order for us to be able to access those additional fields in our analysis. And so that's exactly what this is representing here, where there's only one record per product ID here in this relationship, whereas there's multiple lines associated with a single product at the core table or this order details table. Again, kind of keeping it high level, but now we've got this ability to utilize these tables alongside each other in analysis. We can come into our canvas and, say I want to create, a visual that displays total sales dollars by customer, and I want to be able to visualize over the 3-year period, 22 or whatever the years are that's in this data, I can't remember. So, that's leveraging 3 different tables, but because they're all related and because we're going to invoke the fact table or that central table by pulling in sales dollars, we're able to access the other dim tables as well. So let's pull in total sales. It doesn't have to go in this order. I'm just kind of pulling that in first. And what did I say? By customer, I've got the name is company. So I'll come in and add it here. You can drag it in. It doesn't really matter. So as you can see, it's breaking out the total sales dollars by customer. It's suggesting a visual type. I don't really like that. I'm just going to click over to the matrix. You'll see here I've got the on object interaction to build out my visuals. It doesn't default to this. I believe this is still a preview feature. I can create another video that walks through the differences and why I prefer this route, but that's for a different discussion. But as you can see, I've got the total sales listed out by company, and I said I wanted to look at it by year. So I don't know, let's pick ship year. So if I break out that ship date and I go down and I pull in year to the columns, you'll see that it breaks it out by 96, 97, 98. My years were way off earlier when I said 2002. You'll also see that there's this blank column. So this indicates to me that the core data is missing ship date data because it's not represented here. Either that or the date dim is limited to dates that exclude a range that exists in that core table. So we can actually click over to the table view. I've already got it highlighted here because I went off camera and looked at this, but when I filter this, you can see that there's a bunch of blanks for ship date. And if I click on that, you'll notice that all these order IDs don't have a ship date populated. So that's going to be a data issue, and that's something to explore separately, but that's what that's indicating there. But overall, if I collapse all these, I've got my visual highlighted. It indicates with this green check mark that we're leveraging data from 3 separate tables, and that is only because our star schema model has been designed effectively based on how a star schema model should be designed. So now that we've kind of gone through a bunch of the practical elements of this, I want to kind of jump over to a quick slideshow and just walk through some of the definitions very quickly, but just provide some technical definitions in this video. So here we've got a slide. So this is kind of the standard format or how a star schema data model is structured. So you've got that fact table in the middle, or that hub that kind of contains the most granular data that's required to build out a model. And then you've got the dimensions on the perimeter. I've got this visual over here that kind of displays why it might be called a star schema model. It's sometimes called a hub and spoke model as well. All right, so let's define what a fact table is. So the fact table is kind of our central hub or central table in our star schema model, and it typically contains primarily 3 types of columns. So we've got our line level IDs. So in this instance, we're talking sales data. So we've got the sales order number, also broken out by the order ID and the line ID. Then next we've got quantitative information for analysis. So as seen in our data, we have the sales quantity, the unit price, the total sales, etc. That's what that would be referring to. And then lastly, we've got foreign keys or surrogate keys, which in this instance, we just use IDs that match to the product, customer, supplier data, etc. But like it says here, it correlates to a value in those dimensional tables. And in the dim side of things, they're called primary keys, and this allows for a relationship to be established. Now I'll mention we also have those date fields in our core hub table. That would kind of fall under the foreign key or surrogate key. Typically those would be formatted in a more optimized manner that would get treated more as like a typical surrogate key. But in this instance, those kind of fall under that key category because it relates to those other date tables that allow for us to access additional fields such as year, quarter, year, month, etc. Defining dimension tables, which is those perimeter tables, this stores data attributes in a star schema data model, and they contain primarily two types of columns. We've got descriptive information for analysis, so all of that additional information around description, address, city, state, etc. And then we've got those primary keys, which we just defined, which allow us to relate the data to our hub table in the star schema data model. One last thing I want to mention, and I kind of alluded to it, but it's important to note of a star schema data model that the dimension tables are not joined to each other. Obviously, we can leverage data from multiple DIMs alongside each other when we're invoking that fact table, but if we're just pulling in product IDs or product data alongside customer IDs or customer data, that won't work. For example, I've seen instances where people think that if they pull in a customer name and then they pull in the product IDs, that's going to give them all the product IDs associated with that customer name. But you have to invoke the fact table in some regard in order to get accurate results in those types of instances. That gets a little bit more complex, and we can dive into that in another video. But just keep this in mind, because intuitively, if you had a flat file, this would work. But because we are taking this optimized model approach, it takes a little bit more thought in how do you want to achieve that. All right, guys, that's all I've got today for this video around the very basics of the star schema data model. I hope that you benefited from it, whether you're a seasoned data analyst or you're someone kind of brand new to this whole world of data analytics and Power BI. We've got a lot more Power BI content rolling out here in the near future, so I hope you check it out, and we'll see you in the next video.